At the end of the last video, we saw that we could actually get a vector electric field from a scalar potential. It looks something like this. The components of the electric field are equal to the negative partial derivative of the scalar potential, in this case V. And hence we can construct a vector from those negative partial derivatives, the negative gradient of the potential. We want to put this to use on a continuous charge distribution. Consider this. Say we had an infinitesimal charge element dq acting like a point charge, and hence its potential would be k dq over r, just like a point charge of value infinitesimal charge dq. The potential due to all such elements, if we were to integrate them all together and add them together, would be equal to the integration of all these such elements dv, k being a constant. We'd have k integration of dq over r for our continuous charge distribution. Well, let's try for a ring of charge, a ring of continuous charge distributed around its perimeter. And we want to find the potential at some point P that is a distance x from the center of the ring being a radius a. So dq is a distance r away from point P, and so is every point along this ring as we go around it. Every point is going to be the same distance r away. So we would say our potential is equal to k integration of dq over r, but r is going to be constant because it's not going to change as we go around this ring. So we can take that out of the integral, and so we would have k over r integration of dq around this ring, and hence our potential would simply be kq over r. It would look like a point charge. In fact, if we were at point P, the potential that we would experience would be no different than if the ring of charge were a point charge located a pure distance r away from where we are. We wouldn't be able to know the difference. Let's put this r in terms of x, which actually is a variable that we can use as far as going away from this ring. So as we look at this right triangle, r is the hypotenuse, and it should be equal to x squared plus a squared, where a is a constant, is the actual radius of the ring. X is a variable, so that x is going to be what we're going to be changing. So now our potential looks like kq over r, which is going to be kq over the square root of x squared plus a squared. And we want to find the electric field due to this potential as a function of x, because x is variable here. Well, according to our negative gradient, the electric field is a negative derivative of the potential with respect to x. X is the only variable that the E field is depending on, so we only have to take the derivative with respect to x. So in this case, our potential is kq over the square root of x squared plus a squared. Take the negative derivative with respect to x of that. This is 1 over x squared plus a squared to the 1/2 power, which would be x squared plus a squared to the negative 1/2. As we decrement that power, it becomes a negative 3/2, and the negative 1/2 comes out front. And then by the chain rule, we have to take the derivative of what's inside, which will give us an additional 2x. Negatives cancel out, and we end up with a 1/2 times 2, which cancels out, and we have a kqx over x squared plus a squared to the 3/2 power I being the vector, the unit vector that we add when we do that gradient. So there's our E field as a function of x due to a ring of charge. It's along the positive x axis, and there is no transverse component. This is exactly what we found in chapter 23. How about that? 23, we had to integrate in a very difficult way and make some assumptions about the transverse components canceling out and all that stuff. Here it was very easy. Found the potential, took its derivative, found the E field. Much easier to take derivatives than it is to have to integrate and come up with the same answer that way. So this should make you appreciate the energy approach to electrodynamics. Let's try on another example. What about the potential a distance x away from the end of a charged rod? That would be k integration dq over r. In this case, our dq is equal to our charge per length, lambda, times dr. So it's dependent on r. Lambda is a constant, so we can take that out of the integral, but we're going to integrate dr over r from one end of the rod to the other end of the rod. It's from x to L plus x. Excuse me. So if we do that, we're going to get k lambda. Dr over r integration is going to be the natural log. Evaluate it from x to L plus x. And that will give us k lambda natural log L plus x divided by x. That's our potential, a distance x away from one end of this rod. So we want to find the electric field, negative derivative with respect to x of the potential, and give it a unit vector I. In this case, that would be the derivative with respect to x of k lambda natural log L plus x over x. The k lambda is constant, so that'll come out. And we'll end up with a negative k lambda 1 over L plus x minus 1 over x as we take the derivative of the natural log. Let's find a common denominator for these two fractions. So we'll multiply the first one by 1 over x and the second one by 1 over L plus x. So we'll end up with a negative k lambda. In the numerator we have x minus L plus x over a common denominator of x plus x, L plus x times x. In the numerator, the x minus x is going to cancel out, and we have negative k lambda L over L plus x times x. This is actually the same result we got in chapter 23 again. So again, very easy to figure out the potential. It's a scalar potential, so it doesn't depend on direction. And then from that, we can derive the electric field by taking the negative gradient of the potential. Much easier to do, an easier approach, something that we can appreciate. All right, here's something. We're going to finish up some thoughts here in electrodynamics. Here's the Van de Graaff generator. Consider that Faraday ice pail effect that we talked about earlier, where we would have some kind of conveyor belt bringing in charge, and the charge eventually would be distributed to the outer surface of our ice pail, of our conductor. So we could keep on bringing in charge and keep on adding that charge to the outer surface of this sphere, and hence the charge will build up as far as it can get away from the rest of the charge. It'll build up right on the surface of this sphere, and the E field on any conductor is going to be perpendicular or normal to that surface. So there's going to be E field normal all the way around this surface, and it's going to get larger and larger as the charge builds up. If you were insulated from ground and you were to put your hands on this generator, the charge would flow through you and try to go to your extremities as far away from like charge as possible. So if it were to go into your hair, it would go into the tips of your hair and try to get away from the other charge as best it could. Hence your hair would stand up on end as the charge was trying to repel itself from the other charge. So it looks something like this. Easier to demonstrate if you have hair. And here's somebody who has hair. So here they're touching the Van de Graaff generator. They're insulated from ground, so they're part of this charge. And it's gone to the ends of her hair, making it stand up on end. Potential of a charged conductor. Here are a few ideas about a charged conductor. The electric potential is a constant everywhere on the surface of a charged conductor. How is that possible? Well, we know that this charge is going to accumulate everywhere on the surface, and the E field will be perpendicular to that surface everywhere. So it's going to be perpendicular to a path that you would take as you were going along the surface of this conductor. So there will never be an E field along the direction as you go along the surface. Hence, there won't be any work done as you move a charge from, say, point A to point B. If there's no work done from point A to point B, your change in potential energy will be zero, and hence your change in potential will be zero. Hence, VA will be equal to VB. The potential at point A will be the same as the potential at point B. The charge on the surface of a conductor is constant. The electric potential is constant everywhere inside a conductor. Well, we know inside a conductor, if you have a conductor, the charge will move. It can't reside inside because it's going to be repulsed by light charge. So it's going to move as far as it can away. It's going to move to the surface of the conductor. Hence, if you were to apply a Gaussian surface inside the conductor, you would never enclose any static charge. Hence, there will be no electric field. So inside a conductor, there is no electric field. We know that the change in potential is equal to the integration of the electric field dotted with our path. And if the electric field is zero, that means our change in potential is zero. Hence, if we had two arbitrary points on the inside of this conductor, VA and VB, the change in potential between those points would be zero. Hence, potential A would be equal to potential B. So the potential inside a conductor is constant. Likewise, we know the E field is the derivative of the potential, negative derivative, if you will. And if the potential is constant, then the derivative of a constant is what we expect, zero. So the E field is zero inside. The potential at the surface of a conductor is equal to its value inside. We know the surface is constant. We know inside it's constant. We could select 2 points, 2 internal points, arbitrarily close to the surface. And we conclude we can get as close to the surface as we possibly can. And because of that, there's no reason why the surface would be any different from a point just inside the surface. So the potential inside a conductor is not necessarily zero. It's constant all the way through, even through to the surface of the conductor itself. So, one last thought about the potential of a charged conductor. Here we have a conductor, and maybe the music is particularly inspiring, so he's pretty wrapped up into it. He's pretty charged up, and you can actually see he's really inspired by this music. The first celloist notices this too as well, and she starts thinking, as a conductor, he has potential. Okay, let's end our treatment of electrodynamics with that idea, and we will go on now into chapter 26.